All right, now if it happens that the equilibrium is in gas phase, a lot of times it's much easier to measure concentration in terms of pressures, partial pressures, rather than molarity. So we can actually do an equilibrium constant called Kp, where we do all the concentrations in terms of pressure rather than molar concentrations. So we can actually this is just showing you that pressure is directly related to molarity. So if you have PV equals nRT and you divide both sides by V, we get that pressure equals N over V times RT. R, of course, is a constant, and if we're at a constant temperature, then T is a constant as well. So we can see that pressure is directly related to molarity, moles per liter. So we can rewrite our equilibrium constant using pressures. So this picture is just showing the relationship between pressure and concentration. So on the left, we have 12 molecules in this large volume. So concentration is low, pressure is low. If we decrease the volume, we still have those 12 molecules, but it's in a much smaller volume. And so our concentration is much higher and our pressure is also much higher. So it's just showing the direct relationship between pressure and concentration. All right, so we can express the gas phase equilibrium in terms of partial pressure. So Kp is actually, so if we take the same equation we were looking at before, and instead of doing molar concentrations, we do partial pressures. So the partial pressure of CH4 times the partial pressure of H2O divided by the partial pressure of CO divided by the partial pressure of H2 cubed because of the coefficient. It's really the same thing. It's just concentration in terms of pressure rather than molarity. So this is a Kp. Kp and Kc are very closely related to each other. So sometimes they are different. Sometimes they're the same. Because of this RT value, the Kp and the Kc are equal in this way. So Kp, the value for Kp equals the value for Kc times R times T. R is the ideal gas law constant, 0.0821 liters atmospheres per mole Kelvin. And T, of course, is the temperature in Kelvin. And that delta N just means how many gas molecules. What is the change in gas molecules over the reaction? So delta N is the sum of the moles of gaseous products minus the sum of the moles of the gaseous reactants. So in that previous reaction, we had 4 gas molecules of reactants and 2 gas molecules of products. So delta N would be -2. 2 minus 4 or -2. Let's look at this reaction. So the Kc for the reaction is 2.8 times 10 squared, or 280 at 1,000 degrees. What is the Kp at the same temperature? Well, again, Kp equals Kc times the quantity RT raised to the delta N. So we really only have to figure out what is delta N. And it is 2, because there's 2 molecules in the product. There's 3 gaseous molecules in the reactant. So 2 minus 3 is -1. So now we can simply substitute Kc, R, and T raised to the -1. R is 0.0821 liters atmospheres per mole Kelvin. The temperature in Kelvin, it was given as 1,000, so we just plug that in. Okay, so now all we have to do is plug it into these numbers into the equation. So Kp is equal to Kc, which we were given 2.8 times 10 squared, or 280. R, 0.0821 times T, 1,000 in this example. So 0.0821 times 1,000, and that quantity raised to the -1 power. If you plug all that in, you get 3.4. So the Kc is 280, the Kp is 3.4. It doesn't really matter if you're using concentrations in terms of molar concentrations, you want to use the Kc. If you're using concentrations in terms of partial pressure, then you would use the Kp. And it's all related to the number of gas molecules. Okay, so what happens when we have what happens to the equilibrium constant if we add reactions together, or just if we reverse them or do anything to them? So this is going to be a similar method to what we did using Hess's law in chapter 6. We can combine equilibrium reactions where we know the values of Kc, and then when we add reactions together, what's going to happen to the Kc? Well, remember with Hess's law, if we reversed a reaction, we had to manipulate the delta H's. So with Hess's law, if we reverse a reaction, the delta H became the negative. If we added values together, we could add the delta H's together. Well, K is going to be just a little bit different. So what happens if you reverse a reaction? Well, remember that it's products over reactant. So if you reverse the reaction, you're now going to have what was formerly the products be the reactant. So you're really inverting the value of K. You're taking it and inverting it upside down. You take the fraction and it's 1 over whatever the Kc value is. If you multiply a reaction by a particular coefficient, for delta H, you multiplied that delta H, but for K values, you have to raise it to the power, to the same power. So if you multiply a reaction by 2, that means the K value will be squared. If you multiply a reaction, everything by 3, that means the K value will be cubed. If you divide each coefficient by the same number, then you're taking the corresponding root. So if you divide everything by 2, then you're taking the square root of Kc. And then finally, if you add individual equations together, what you have to do is multiply the K values to get the overall Kc. So let's see if we can do an example. All right, so for example, let's take a reaction 1. N2 plus O2 gives me 2NO, and my K value for that is 4.1 times 10 to the minus 31. All right, let's evaluate that for a second before we move on. That is a really, really, really tiny K number, and remember what we said about very small numbers. If you have a very small K, that means the reaction doesn't really go as written. It means that the reactants will be so much bigger than the products because the denominator dominates. And that's a really good thing. So we got a lot of nitrogen and oxygen hanging out in our atmosphere, and if they spontaneously formed NO, we would not be living too long. So that's interesting that that K value is very, very small. All right, then let's look at this other expression, N2 plus 1/2 O2. Again, a very small K value, giving us N2O. But the question says, let's use these two equations. Let's find the Kc value for the formation of NO from N2O. So let's take the first two equations and combine them somehow to form that third equation. So if you remember Hess's law, or even if you don't, the idea is to take the first equation and line something up in the way that you want it to be. So for example, if we look at equation number 1, N2 plus O2 gives us 2NO. In the final equation, we also want 2NO on the right. So actually, if we leave this equation as it is, it will line up to put the 2NO. Since that's the only place NO shows up, if we keep it on the right-hand side and keep the 2 in front of it, it'll work. So if we rewrite N2 plus O2 to give us 2NO, and we know the K value for that is 4.1 times 10 to the minus 31. Now, we want to get the N2O on the left-hand side. So notice that in equation number 2, the N2O is on the right-hand side. What if we flipped that the other way around to get the N2O on the left-hand side? So if we flip that, we have N2O gives us N2 plus 1/2 O2. What do we have to do to the Kc? We have to invert it. So the new Kc will be 1 over 2.4 times 10 to the minus 18, which is 4.2 times 10 to the 17. Okay, so this shows it again. So we took equation number 1 and we left it alone, and we left the K value alone. And then equation number 2 we reversed. And when we reversed that equation, we did the inverse. So 1 over 2.4 times 10 to the negative 18. Now, if you look, what's going to happen? We have an N2 on the left and an N2 on the right, so they cancel. We have the N2O on the left, which is where we want it. We have one O2 on the left, a half O2 on the right, so actually a half of them will cancel, so we end up with 1/2 on the left. And then we have the 2NO on the right. So in order to get the K for this expression, which is what we were looking for, we have to multiply the two KCs from number 1 and number 2. So number 2 is the one we already manipulated. So 4.1 times 10 to the minus 31 times 1 over 2.4 times 10 to the minus 18th will give us 1.7 times 10 to the minus 13. And that's the K value for the final equation number 3. All right, just a few other things before we really get into the nitty-gritty. A heterogeneous equilibrium is one that has reactants and products in more than one phase, so solids, liquids, gases. Now, if you have a solid or a pure liquid present or a pure solid, they really don't affect the equilibrium at all, and so we don't include them in our equilibrium expression. So the concentration of a pure solid is considered to be 1, and so it doesn't appear in the equilibrium. So for example, here's if we have this reaction, carbon solid plus H2O gas gives us CO gas plus H2 gas. If we want to write the equilibrium expression for that, it would be products, CO times H2, divided by reactants, H2O, but we don't include any pure solids. We only include gases or aqueous. We don't include pure liquids, and we don't include pure solids. All right, what if we have a situation where we have particular concentrations of reactants and products and we want to know, is this reaction at equilibrium? And if not, which way will it shift to get to equilibrium? The way that we're going to do that is to substitute the concentrations into the reaction quotient, and we're going to compare it to K. So what is the reaction quotient? Well, we're going to call it QC, so reaction quotient, QC. It's an expression that looks just like the KC expression, only we don't know for sure if the concentrations are at equilibrium or not. So we're going to show it looking just a little bit different. So for a general reaction that we saw before, AA plus BB gives us CC plus DT. We know that the K expression is products over reactants raised to their coefficients. Well, we're going to also do the same thing for the QC expression. So the QC just says the concentration of products raised to their coefficient divided by the concentration of the reactants raised to their coefficients. Well, we put that little I there because we're saying, okay, we don't know if that's at equilibrium or not. We're going to call that initial. We're going to say it's at some concentration that we don't know if it's equilibrium. So it turns out that once we plug the numbers in, if that Q value is greater than Kc, that means we're not at equilibrium and the reaction will shift left. Because if Q is bigger, it needs to get a little bit smaller. So it's going to try to get smaller. It has to put more into the denominator, which means we're going to the left. We're going to reduce the number of products and we're going to increase the number of reactants, which means the reaction will shift left. If Q is less than C, that means that the value has to get bigger to get to its set point. So to get bigger, we have to put more in the numerator. So that means the reactants will decrease and the products will increase. So this reaction will shift toward products to get to equilibrium. Of course, if Q equals K, then we do know we're already at equilibrium. So let's do an example. N2 plus 3H2 gives us 2NH3. So we have a 50-liter vessel. We have 1 mole of N2, 3 moles of H2, and 0.5 moles of NH3. First of all, is this at equilibrium? And if not, which direction, toward reactants or toward products, will the system shift to get to equilibrium? The Kc for this reaction is 0.5, so that's important to know. So what we're going to do is find the Q value. We have to be really careful because we do remember that those brackets mean molar concentration. So if they give you moles and they give you volume, make sure and find the molarity first. So we know that there's 1 mole of N2, 3 moles of H2, and 0.5 moles of NH3, but we want to divide by the volume, 50 liters in this case. So either you'll be given the molarity or you'll be given the moles in the volume, and you do need to divide by the volume because they don't cancel out since the values are sort of different in the numerator and denominator. All right, so the nitrogen is 0.02 molar, the hydrogen is 0.06 molar, and the ammonia is 0.01 molar. So let's plug those into our Q expression. There's our Q expression, NH3 squared over N2 divided by H2 cubed. Plug those and we get 23. So first of all, we know 23 is not 0.5. So we're not at equilibrium. We also know that Q is greater than K. So what does that mean? If Q is greater than K, to get to equilibrium, it has to get smaller. To get smaller, it means it has to it has to put more in the denominator. The denominator is the reactants. It's going to shift left to produce more reactants and to decrease the number of products. So if Q is greater than K, it will shift to the left.